All right, everybody, it's about 10 o'clock, according to my clock anyway. I'm going to go ahead and get started. It's good to see all of you. Welcome back. I hope that you had a nice weekend. I had a pretty good weekend, except that yesterday I decided to go hiking because I've been working so hard all weekend grading exams and stuff. And my hike turned out to be 25 miles because I had to park way at the bottom of the mountain. I climbed to the highest point in Orange County, which is, you see it every time you drive down the 5 or the 15 freeways heading south from here. It's just kind of right there above Irvine or Lake Forest or whatever. The problem was that the gate was closed. So I said, well, I'll park at the bottom and just walk all the way up. Well, it was 25 miles and took the entire day. And I got these blisters on my feet. So walking around even right now is kind of a little bit dicey for me. So I'll be doing my best. We'll see how my feet hold up for 2 hours of this. But anyway, I hope that you guys had maybe not quite that adventurous of a weekend. But it's good to see all of you again. Let's see where we're at. We've finished the first 1/3 of the class. I kind of break it into 3 parts based on the exams. And we just finished our first exam last week. I did grade your exams. I'm sure you know that already. I talked to you about that in my email, and I will give you back your exams, but I do it at the end of class because if I do it right now, everybody just looks at their exam and doesn't listen to me. So I'll give those to you in a little while and talk about that. But let's talk about where we're going forward from here. There is just one homework assignment due this week. Now, unfortunately, I have to go out of town on Friday for a work trip. So my normal Friday deadline with Friday office hours to help people out isn't going to work for me this week. So I would like to try to get the assignment done by Thursday night. If we get here on Thursday and everybody's like lost on the homework and we need more time, you can let me know that. We'll take questions during class on Thursday on that assignment. So I really want to encourage you to start on it early and come in with questions and put them on the sideboard. It's been a little bit of a slow startup this particular semester with getting people to do that. So I'm going to try this week to take questions on Thursday in class about the homework. Some of the homework for this assignment, I actually did those examples in the video that you watched. And some of the other ones are actually going to show up today as well. So it's not as much as you might think in terms of doing original problems. But as you saw already in the video, there's a fair bit of a write-up that goes with these subspace examples. You have to really spell things out a little bit. So it does take a little bit of time, if nothing else, to kind of get through those things. I did want to thank you all for watching that video. Super, super good. I know it was a long video. Maybe some of you watched it on double speed. It's okay if I talk kind of fast that way. But at any rate, I hope that you got a lot out of it. It does help, I've found in the past few semesters of teaching this class, to springboard us into this new chapter. Guys, this next 1/3 of the class does get compressed a little bit. We have only 7 lectures between now and our next midterm, believe it or not. So our next midterm is on March 19th. So we have quite a bit to cover. We're going to cover all of chapter 4, which, by the way, is 10 sections. It's a long chapter. And then chapter 5 is much shorter. We'll have a couple of lectures on that. And then the other thing that we will have in this next part of the class is just the very beginning of chapter 6, the first section, which is on linear transformations. So that's kind of what's up ahead of us in these next 4 weeks or so. Okay. What I did today, any questions before I jump in today, guys? So far, so good. Okay. What I have done, as I always do, is I put a recap up on the board, but this time, of course, it's a recap of the video that you watched. I want to review the highlights of that, and then we're going to practice some more examples that are of that same nature again. This is a total left turn in the material because this section is much less computational. It will be much more writing and conceptual and thinking about things a little bit. So we need to spend a little time getting used to it. The whole point here, guys, is the idea of a vector space. If you look in Canvas, there is a handout in the special handouts folder that's just simply called vector space axioms. And that's this handout right here. I think I linked it to you in one of my messages that this would be good to kind of keep in front of you while you're looking at the video. A vector space, guys, it is just an abstract mathematical framework. It's an apparatus that mathematicians have sort of stolen from the real numbers and from R2 and from R3. They've stolen it from your experiences in calculus to sort of grab the rules that you're familiar with. Axioms is just another word for rules, right? The vector space rules are just stolen from the familiar, the XY plane and the real numbers and things like that. And they've grabbed 10 of the rules out of that familiar context, and they've said, hey, let's adopt these rules as the framework for many other kinds of mathematical structures. And these structures are called vector spaces, right? There's going to be 10 rules. Every vector space has a set of objects, which are called vectors, and has two operations with it, which are called addition and scalar multiplication, right? Along with all of these properties here. Yeah, most of these properties are just pretty standard, obvious properties. Commutativity of addition, you're not going to hear me talking about that very much. Associativity of addition, not going to hear me talking about that very much. But there are two of these 10 rules that are ultra important, right? Which are the first two. The first two, A1 and A2. And these are called closure under addition and closure under scalar multiplication. I sometimes abbreviate that as CL plus and CL with a dot. And these are just A1 and A2. Okay? So I'll come back to that in a second. But this is a big list of 10 rules, most of which you won't ever have to concern yourself with. Because most of the time, guys, these rules are going to be automatically true for whatever problem you're working on. And why do I say that? Well, the reason that these axioms are almost always going to be true, guys, is that we are almost always going to be working in one of these standard universes. These are the familiar vector spaces. I put them all in the video. These are like the most common vector spaces that we have. The first one is Rn. This is the one that motivated the whole thing, right? Calculus is done in R2 or R3 almost all the time, right? So Rn is an extremely familiar vector space, right? And so, of course, all of these rules are true for Rn because we stole these rules from what we know about how Rn works already. So we're just grabbing what we already know and just laying it out in a list. That's what this is. And then we're realizing that that same list also works in the universe of matrices, right? And it also works in the universe of polynomials, which I wrote down in the video as well. Pn of R is polynomials. It also works in the universe of continuous functions. So you can take just all the calculus functions that you know, and you can imagine forming a vector space out of those. In each case, we have an addition operation and we have a scalar multiplication operation. And those operations are just done in the standard way. So if I want to add two m by n matrices, I do it slot by slot, the way we learned a few weeks ago. If I want to do scalar multiplication, I just multiply the scalar through all of those slots. That's how it works, right, in that universe. Each of these universes has addition and scalar multiplication that comes with it And those operations are done, guys, in just the natural standard way that you would ordinarily do it. Now, believe it or not, it is possible to define a valid vector space with some of these vector spaces where you do a weird addition or scalar multiplication, right? Where you make up a new definition of it. And you'll find some of those examples in our book. I used to, way back in the early days, I would go over that in 250B. And I realized that most engineers are never going to need that. You're never going to see these weird operations on vectors. It's always going to just be standard, just the way you ordinarily would add or scale or multiply. So I decided not to bother my 250B students about those examples. Instead, you'll find those in Math 307. If you take more of a math-based theoretical linear algebra class, you're going to see some of those weird operations being used. But for us, everything is just going to be standard, right? The vectors are familiar to us already, and the addition and scalar multiplication are done in just the obvious natural way that we've already learned. Okay. So far, so good? Now, one thing, just as a side note, this is a little bit weird, but in a vector space, you do not have regular multiplication. You only have scalar multiplication. So I realized that just earlier this month, I explained to you, for example, how to multiply matrices together with that whole dot product matrix multiplication scheme. Well, guess what? When we're in a vector space, we don't have that anymore. We're not doing matrix multiplication. We're only going to do addition and scalar multiplication. So what it basically means is I'm going to ignore what I just taught you earlier this month. Sounds kind of weird, but we're going to pretend, at least in this particular framework of a vector space, we don't multiply vectors together. So that matrix multiplication that we learned, kind of irrelevant right now. Okay, at least for a while, right? For right now, we're not going to worry about that. That's why, for example, my matrices don't have to be square size. M by N is fine. If I tried to do regular multiplication, that wouldn't work. You can't take a 3 by 2 matrix and multiply it by a 3 by 2 matrix. That wouldn't even be the right sizes, right? But I can get away with this as a vector space because I'm not going to do matrix multiplication. I'm only going to do addition and scalar multiplication for right now. I'm going to strip away anything else that I might know. I'm also not doing division. I'm not doing inverses, like all that other stuff. We're kind of just dropping it for now. And we're saying that at least for the purposes of this framework, that's not an important piece of it. Okay, so these are the standard universes that we're going to be working with for the most part. But you could make up a weird universe. I know I had an old exam in this class a few years ago. I wrote up a problem where the vectors were just the colors of the rainbow. And I gave a definition. I said, okay, green plus purple is equal to black. And yellow plus yellow is equal to white. And I did all this. I made a little table. I gave it to the students. They hated it. Okay, so if I want to fill out this table, what do I get for the results and stuff? It was kind of a weird problem. That was, again, kind of not standard. That was me kind of just trying to show how abstract this vector space framework can really be. But again, these are not the universes that you guys are going to work with in your everyday life. So I tend to shy away from those generally. But what I do want to say, guys, is that actually the big universes that are listed here are generally, you should think of them as just being in the background of whatever problem I'm going to ask you to solve. What's really going to end up being more important than this big background universe is going to be the subspaces that we create within it. Okay, I'm going to give you several examples of this in a few minutes. Guys, a subspace is just a vector space within an already established universe. Because you can have a vector space within a vector space. And if that's the case, we call it actually a subspace. I had a student ask me, well, I have students ask me this almost every semester. What's the difference between a vector space and a subspace? What's the difference between a vector space and a subspace? And in fact, you want to know the honest truth? I asked my professor that question when I was learning this stuff because I couldn't tell what the difference was. It's actually a little subtle. They're really the same. They're really the same. When I say that something is a subspace, I'm really saying that it is a vector space, but that it's within a bigger vector space. You saw me draw the picture, right? Where I drew the V like this, and then inside of it was the S, right? In the video, it's just one vector space inside of another one. The beautiful thing about the subspace, though, the beautiful thing with the subspace is that it inherits almost all of the rules on that list from V. If my big universe V is already a vector space, then S inherits, I think, 8 out of those 10 rules almost, 7 or 8 of them. And which means that to check if you have a subspace, you really only have to worry about the closure axioms. Those are the ones that don't get inherited for free and that we have to actually check. And so you saw me do that in the video, right? The n by n symmetric matrices. That's a subspace of the n by n matrix universe where I have all of the n by n matrices, right? So within that, I have just the symmetric ones, okay? But in the video, I had to check, well, is it really closed under addition? And is it really closed under scalar multiplication? You saw me write it out. I actually wrote down those verifications. So you have to write that much down. But the good news is you don't have to do all 10 of these rules, which would take, well, a lot more time, right? You don't have to do all of that because most of those rules, such as, you know, commutativity of addition, associativity of scalar multiplication, those rules just get inherited by the subspace from the big universe. If something is true within the big universe, it can be inherited by everything inside of it. If I tell you that everybody in the state of California has a driver's license, I know that's not true, but if everybody in the state of California has a driver's license, well, then it would be true for me to say that everybody within Orange County has a driver's license. I'm saying something that's specialized within the broader statement that I already made. So that's just comparing the subspace with the big vector space. Yeah. Another good example from the video, this was towards the end of the video, is the idea of the null space of a matrix. Just to be clear, guys, you guys already know how to calculate null spaces. And actually, this is not new. This is just solving a system of equations, which is something we've been doing since chapter 2. So you're going to see some homework problems. They're going to say, find the null space of such and such a matrix. If they say that, all they're saying is take your matrix and augment it with a column of zeros and then just solve it by back substitution. Okay, that's all it's asking. So just be aware of that. Sometimes I think people they see this word null space and they're like, oh, this is some totally new thing. Actually, it's not. It's something we've done before. But when you're looking at the solutions, the X vectors that solve that system, they live in the big universe of Rn, right? So Rn is one of my big universes over here. And within that, we're looking at the solutions to a system. Okay, this is why I was saying just a couple minutes ago, guys, that we often care less about the big universe that's in the background and more about the subspace itself, which is the vectors that are actually, solving my system of equations. That's actually what I care about. So in some ways, these null spaces are more important than just the big universe of Rn that's kind of in the background of the whole conversation. Yeah. And by the way, guys, in the video, I confirmed, and you took notes on it, I confirmed that the null space of any matrix is always closed under addition and scalar multiplication. In other words, I already confirmed that the null space of a matrix forms a subspace. Always. Doesn't matter what the matrix is, doesn't matter what its size is, doesn't matter what numbers are in it. If you recognize that somebody is asking you about a null space of a matrix, boom, you can just say, yep, it's a subspace. Because basically, we showed it in that video. There's really only one person in this room who will ever have to verify again that a null space of a matrix is a subspace. And you know who that's going to be? Me. 6 months from now, when I teach this class again, and the new people want to see, oh, well, why is the null space a subspace? Well, I'll have to show that again, right? Basically, has to be verified once. You only have to verify it once. And I already did that for you. So from now on, all you ever will have to do, if you see that you are looking at a matrix or a null space of a matrix, you say, yep, it's a subspace, because that's a fact. It's a fact from those video notes that we are already aware of. So those are a couple of examples of subspaces. Let me give you one more that we're going to practice in a minute. Anytime you solve a differential equation, right? That's half of what this class is supposed to be about. If you solve a differential equation, you are working in the universe of calculus functions. But we don't care about all of the calculus functions. I just care about the ones that actually solve that differential equation. Well, guess what? They form a subspace. They will form a subspace. And so all of this vector space theory that we're going to do for these next few weeks is going to apply to those solutions to the differential equation. It's actually one of the many reasons why we put these two subjects together. It's why we learn these two subjects together. Super, super important. Any questions so far, guys? That's kind of my 10 or 15 minute review of kind of what was in the video. Yes, Austin.
I don't know if this doesn't make sense, but when you're looking at a vector space that's in 3D and you give you a subset in 2D, would the subset always be
a subspace?
Yeah. Would it always
Have you already started looking at the homework?
I was looking at the notes and then I looked at the group.
Okay, okay, cool. There is actually a homework problem that asks you, is this is just R2 basically. Is that a subspace? So is this a subspace of R3? Of course, R3 would be the set of X, Y, Z. Something like that. People will ask me, is R2 a subspace of R3? The answer is no. They are not even compatible with each other. It's like apples and oranges. It would be like if I asked you, would the colors of the rainbow form a subspace of the universe of different kinds of fruit that we have in the world, right? The answer is no, they're not compatible at all. They have no relation to each other, so I can't really compare them. So I think that's your question. The answer would be no, they're not related at all. Now, the one in the, I think that the one, I can't remember that's quite what it's a true false item on Thursday's homework.
So it's XY compared to XY0.
Ah, okay. So I put 0 here. There we go. So I created this set here as to try to make it look more like this. And I said, is this a subspace of this? The answer is still no, because this has 2 slots. This has 3 slots. They're not even in the same universe to begin with. So the answer would be no, that the first one is not a subspace of the second one. This is a no. I think it's false on that true false item for Thursday. Yeah, good question. Other comments or questions so far? In my video, I did a ton of examples. There must have been about 7 or 8 of them. I'd like to do a few more right now, and then I'd also like to do some group work and let you guys practice even a few more. So this takes a little while to get the hang of this. Part of why chapter 4 does drag on a little bit is that every concept about vector spaces that we have you're going to need to practice it not once, not twice, not 3 times, but sort of every universe that you have, you're going to need to see how it looks in that case. Okay, so if I'm doing subspaces in polynomials, how's that going to look when I write it up? Versus if I'm doing subspaces that have slots in them, how is that going to look when I write it up? Just the way the notation is and how it visually gets laid out on paper kind of takes practice, in each of these contexts. So I'm going to give you even more practice right now. So let's do some warm-ups. I'm going to give you a vector space, and I'm going to give you a proposed subspace. And I'm going to ask you, is it a valid subspace? So let's do the first one. Number 1, B is equal to Mn of R, and S is the set of matrices capital A in V. So these are going to be n by n matrices such that the determinant of A is equal to 0. And the question is, would those matrices form a subspace of B? Now, another thing from the video that I forgot to put up into my recap here is that axiom A5, which says that there always has to be a 0 vector, is an easy one to check at a glance. Like you can glance at this and you can ask yourself, is the 0 vector in the set? So I like to do this 0 vector check. Technically, it's not required, because technically, if you check the closure under addition and scalar multiplication, that actually buried within that, you would be also confirming the 0 vector. So you don't technically have to do this 0 vector check, but I like to do it because if the 0 vector is not in your set, it is already game over. It is not, if any one of these axioms fails, it is not a subspace and you can stop. And this is an easy one to check. So what do you guys think? With the 0 vector, so first thing I have to figure out was, what is the 0 vector? All right, well, I'm working in the universe of n by n matrices. So the 0 vector for that is what we used to denote as 0 sub n, just a big group of zeros. And do you think that that is an element of S? In other words, would it meet, this is the condition here for being in S, is the determinant of the matrix of all zeros, is that equal to 0? Absolutely. If your matrix is completely filled with zeros, that is equal to 0. And so the conclusion of that is that the 0 vector is in S. I'll put a little check on that. Now, again, if this had failed to work out, we would have been saying, no, it's not a subspace, and we would be done. Okay. The fact that it passes the 0 vector check means that we have to now go on and think about whether it would be closed under addition and scalar multiplication. Okay. Do you understand what I'm saying? This is one of those things. If the test fails, you get a quick no out of this problem. But if it passes, then we kind of have to work a little harder. So let's check the closure under addition. Now, again, if this fails, we'll be able to stop. But if it passes, then I'm going to also check the scalar multiplication. So one of the things that's a little tricky here, guys, is that the way that you proceed with your work, it depends a lot on whether it's a yes or a no as to what you're going to write down. So I like to not just blindly start writing anything down. I like to just stop and think for a second. Would it be true that if I start with 2 matrices that both have a determinant of 0 by themselves, would it have to be true that after you add them together, that determinant would still be 0? I actually think we've done this one before the midterm, because this is about determinants, right? And you probably remember that there was no nice formula for determinants with addition. determinants did not play nice with addition, and that's already a red flag to me. It's like, I don't think this is going to work. I think that this is probably, my gut feeling, we haven't proved it yet, but my gut feeling is that this fails. Even though the zero vector check passes, I think this one fails. Now, to write this up, the way you would write this one up, guys, is you would make a specific example, okay? And we have actually done this before. I even remember I called on some people to give me their 4 favorite numbers, and we made some matrices and added them. So I'm just going to make a new example right now to show that this fails. If I take the matrix A, and you could make many other examples, I'm just going to make a really easy one. If I make this matrix A, which is 1, 0, and 0, and 0, that is in S because the determinant of that matrix is 0. And if I take another matrix B, which I'm going to make 0, 0, and then 0 and 1, that is also in S because, again, the determinant is 0. And now, if I add these together, A plus B, right? If I add them the way we always add matrices, which is slot by slot, and we look at the result, the determinant now of A plus B is 1, which is not 0, which means that this is not in S. Guys, there were some people, I was checking the scanned notes from the video, and there were some people missing some slashes on some of the places. If I put this little slash through the belongs to symbol, that's what you need to do if the element does not belong to the set, right? So I put that little slash there. It's absolutely critical. Okay, so guys, the answer on number 1 is no. This is not a subspace of V because closure under addition fails. I don't even have to check the scalar multiplication because as soon as one of the axioms has failed, it's already game over. It cannot be a subspace. It did pass the zero vector check, but this just goes to show you that even if it passes that zero vector check, doesn't guarantee that it's going to form a subspace. Actually, by the way, it's interesting. These are the matrices that are not invertible. You remember? Back to chapter 3, actually. So the matrices that are not invertible are the ones that have a determinant of 0. One of the examples that was in the video was the matrices that are invertible. And that also did not form a subspace because the zero vector, the zero matrix, isn't invertible. So that one failed because of the zero vector check. So guys, the matrices that are invertible, not a subspace. The matrices that are not invertible, not a subspace. So there's no connection there. Symmetric, on the other hand, that was a subspace. Okay, so sometimes you get surprises like that. Let's do another one. A question first, Stephen.
Go over really quick, just one more time. Why isn't the zero matrix invertible?
Well, what's the determinant of it? It's just 0, and if the determinant is 0, it's not invertible. Yeah, exactly. Okay, anything else?
So basically you're saying that if the determinant is 0, then we should be able to clarify that it's not invertible, right? So
Right, this is going back to, chapter 3. If the matrix has, if I give you a matrix and I want to know is it invertible or not, the first thing I always do is check the determinant. And if it's 0, then it's not invertible.
And if it's not invertible, then it's not a part of the subspace.
Right, these non-invertible matrices, as this blue writing shows us, does not form a subspace. That's very true. Excellent. Let's do another example. Let's do number 2 here. Let's take the vector space. This is my big universe. It's going to be R4. And S is going to be the set of, I'll call these unknowns X, Y, Z, and W. Obviously, I'm going to have 4 slots since I'm doing an example from R4. And I have a couple of equations, X plus 2Y plus 3Z plus 4W equals 0. And then the second equation is 5x plus 6y plus 7z plus 8w is equal to 0. Let's take this think I can probably turn off this screen for now. Okay. So taking a look at this one. Does anybody have any, it's a thumbs up, thumbs down. Is it a subspace of V or not? Does anyone have a kind of a first read on it that they kind of suspect? Yeah, you got your hand up. What do you think?
It is a subspace.
It is a subspace. I am going to go ahead and agree with you. Oscar, is that what you're thinking too?
Yeah.
Yeah. So, Yair, why do you think it's a subspace?
The null space is always.
I love it. Yes, that's exactly the reason. You're looking at a system of equations here, guys. And the system of equations has zeros on the right-hand side. If these numbers were not zero, then it would not have been a subspace. So it's actually very critical what you see right here. As long as that's zero, which is matching with this zero vector right here, as long as that's the column of zeros on the far right, you've got a subspace. So the answer is yes, and I'm just going to say, since S is equal to the null space, you saw me do this in the video too, right? Just doing one more example of it to reinforce it. The null space of, and then you just write down the matrix. 1, 2, 3, and 4 on the first row, and then on the second row, we would have 5, 6, 7, and 8. That's it. And you just want to leave it at that. You don't have to justify, oh, well, why is the null space actually a subspace? Remember, that's what I showed you in the video. You don't have to ever verify that again. If you don't take advantage of this null space fact, and you say, forget it, I'm going to still check that it's closed under addition and scalar multiplication, you'll still be writing 15 minutes later. It's going to take a lot longer to write out those verifications than to just give this quick answer. Yeah.
Can you do like row operation to get to the zero?
If the right-hand side has all zeros to begin with, any amount of row operations won't change that. And if the right-hand side has any non-zero numbers in it, any amount of EROs will not change that either. So it's a really good question. I don't know if anybody's asked me that in the past. It's a really good question. Can I take numbers in the far right that are not zero and turn them into zero? Not in such a way that you could turn something from being a subspace or not. So the answer would be no. Yeah, it's a really good point. So you can just look at it at face value and know the answer. Again, if I change even one of these numbers, and don't do it in your notes or you'll be mixed up now, but if I change even one of these numbers, this answer changes to a no. And why would this be a no now?
The zero vector won't work.
The zero vector won't work, right? 0, 0, 0, 0 is my zero vector, and it would not satisfy that equation anymore. So that's absolutely right. So if you have a system of equations in front of you guys, it's going to be a fast answer. Either a yes fast for this reason, or a no that's fast because the zero vector check fails. Okay, let's do another one. Number 3. Let's take V to be P3 of R. So I'm going to do a polynomial example. P3 of R, these are polynomials of degree 3 or less. So they're going to kind of look like the form of a cubic polynomial. These are sort of like all cubic polynomials. And then inside of that, I'm going to make my S here. And S is going to be the set of, I'll call it P of X, which is an element of V, such that P of X is equal to AX cubed plus CX. So it's polynomials that you could write them out like that. So again, P3 of R, if you're thinking about what kind of objects those are, they would look like, AX cubed plus BX squared plus CX plus D. It's just any cubic polynomial whatsoever. And now I'm creating a set S that has just these polynomials only. Which just means that we're looking at polynomials that have no constant term and no x squared term. You guys with me? Okay, so what is your intuition telling? Well, actually, before I get to the intuition, let's just do the zero vector check. Okay, so the zero vector check, because that's a quick thing we can do really easily. The question is the zero vector in S? Now, the question is, what is the zero vector? So in this universe, in the universe of P3 of R, my zero vector, I'm sure you would agree, is literally just 0x cubed plus 0x squared plus 0x plus 0. That's the polynomial that behaves like 0. If you add this polynomial to any other cubic polynomial, it just leaves it the same. That's kind of how the zero vector is supposed to work. Now, does this polynomial have the right form to be in S? It actually does, because you can just simply not write down the terms that are dealing with the x squared and the constant term. It is just 0x cubed plus 0. And that is the right form to be in S. So this thing does pass that zero vector check. It does pass it. Okay. So if it passes the zero vector check, then we have to go on and think about closure under addition and scalar multiplication. So let's put the closure under addition here, guys. So before we write anything down, I want to just think about the intuition behind this. If I take two polynomials of this form, when I say the form, I mean the a and the c could change. So you could change what those coefficients are, but they have the form of a cubic term added to a x term. If I took two of those and added them together, kind of do it in your head, just kind of envisioning it in your head, do you think you would get something else of the same form back again? Right? So in other words, you start with something that has no quadratic term and no constant term. Then you take something else that has no quadratic term and no constant term. Well, if you add two things together like that, you're never going to get a quadratic term or a constant term. It's going to have that form. I think this probably passes. That's my intuition. I'm going to try to write it down now. Okay, so let's do that. Let's let P of x, comma, Q of x be elements of S. So I start with two things that are in S. Now, again, I want to really emphasize here. You see how when the closure under addition failed, I made a very specific example of it. But now, if I'm trying to convince myself that this is always going to work, I have to keep it very arbitrary. So you notice I'm not making specific P of x and Q of x. I'm leaving them kind of abstract. Now, I need to make sure that they are in the right form. So let's write P of x as ax cubed plus cx. And Q of x is also in the same form, but here's the important thing, guys. Q of x is not the same as P of x, so I should be using different coefficients. Maybe I decide to go with, I don't know, let's go with mx cubed plus nx. Doesn't even matter what letters you use, but they should be different letters. And now let's add them together. So then P of x plus Q of x, if I just add them together, what I'll get, if you'll let me just kind of add them vertically here, I'm going to kind of clean this up a little bit. A plus m, quantity of that times x cubed, and then plus c plus n times x. Now, obviously what I ended up with is not exactly what I started with, but is it of the same form as what I started with?
Yes.
That's what's important, right? That's it. It's something times x cubed plus something times x. It does have the same form. And very important, guys, if you believe it's in S, you need to write that down. So that's the big punchline. The punchline is that, yeah, the result of this is in S. Yeah, Oscar, please.
So with polynomials, you want to make sure that if you have two sets of polynomials,
Mhm.
you add them together, you get the same form.
The same form, the same form. That's exactly right. Excellent, excellent. Let's try the scalar multiplication. Okay, so closure under scalar multiplication. Let's do that one here. Because if it passes the addition, then all I have left to do is check the scalar multiplication. So do you remember what letter I usually was using for the scalar in the video? It was a K, exactly. So I'm going to let K be just a scalar, which just means it's a real number. So let K be an element of the real numbers. And we're just going to say P of X as above. So I'm just going to recopy the, I don't have to make a new polynomial. I can just grab the P of X that we already had. And what I want to do, so this, guys, you could literally make yourself a rubber stamp for the next month that says that on it, and just put it as the first line of your closure under scalar multiplication. And then I'm just going to do this scalar multiplication right here. I'm going to take K times P of X. For this part, we don't really use the Q of X at all. It's just the P of X. So this becomes K times the quantity of AX cubed plus CX. And just to get it looking in the form that I want, I'm just going to multiply it out. So it would be KA times X cubed plus KC times X. It's about as good as it gets. I have it multiplied out, and now I want you guys to all stare at this, take a breath, and ask yourself, does it have the right form? Something times X cubed plus something times X. That's really what the form needs to be. So yes, this is in S, and we put a check there. And now we can say that this one is a yes, right? This is a subspace. This one is a subspace as well. But we had to go through all that work to verify it here. Okay? Does that make sense? Guys, the A and the C that you see here, they are representing generic real numbers. They're not required to stay the same. If I change this problem just slightly, I'm going to make one more related example here. I can totally throw this whole thing off, right? So if I take V to be P3 of R, and I take S to be the set of P of X in V such that P of X is equal to AX cubed plus 5X. So it's almost exactly the same problem as the one we just did, but I made one little change. The change that I made is that instead of a CX here, I specifically put the number 5 there. Is that going to change my answer? No. Let's try the zero vector check. Now, guys, in this universe of P3 of R, my zero vector is still the same, right? My zero vector is still 0x cubed plus 0x squared plus 0x plus 0. That is the zero vector. We have to live with that. Would you look at this and then tell me, is it in S or not in S for this thing? If it's going to be in S, what is the coefficient of X have to be? 5, right? What's the coefficient of X in this zero vector? It's not 5, right? It's not 5. This is not in S. Let's get that slash going through that element symbol. Guys, it fails immediately here. It fails immediately. This is a no.
Would you say that it would work for like it's called this, I don't know how to say it, but
The arbitrary constants.
yeah, it would, right?
Yes, you're going to see this in the homework too. I'm going to have like back-to-back problems where one of them has arbitrary constants and then the next one, a specific number was put in. What I'm hoping you guys are starting to realize is when we put specific numbers here, everything goes bad. Doesn't work. Well, think about it. If you took 5x and you added it to 5x, that's two things that are in S to begin with, you would get 10x. 5x plus 5x would be 10x. Well, 10x is not the right form for S anymore. So it fails that property. Whereas if I just have generic letters in my calculations, everything's cool. So that's kind of the difference. Seem okay? So this is another one of these quick no problems. All right, I have to buck the trend of those mathematicians that try to separate differential equations from linear algebra. I have to give you a maybe I need let's come back over here. I have to give you a differential equation example. We're not really going back to differential equations yet, but I can at least make a nice little example that ties in with that. So number 5. Let's take V to be C of minus infinity to infinity. So that's really just this universe here on the bottom. These are just calculus functions that are just defined on the entire real number line. And then my set S is going to be the set of, I'll call it Y, which is an element of V, such that, and then let's just make this Y double prime plus 3Y prime plus 4Y equals 0. Now, as of this moment in this class, we don't know how to actually solve this differential equation yet. That's not the point right now. In about 2 months, we will all know how to actually solve this equation, which is like the best possible thing we could do. But at the moment, I don't even want to solve this differential equation. I would just like to know, do the solutions to that differential equation, whatever they are, do they form a subspace of V? So let's try it. Let's start with our zero vector check again. The first thing we have to figure out is, do we know what the zero vector is in this universe? So we're working in the universe of calculus functions. So the zero vector, let me maybe just add this over here. In this last universe, guys, the zero vector, I need just a little more room. I can put it right here. The zero vector for this universe, keep in mind, guys, it's not a number, it's a function. This is a universe consisting of functions. So what function is it? Well, it's a function whose graph looks like this. Here's my XY plane. The graph of my zero vector would just be the function, which I'm drawing right now in blue, which is just the function of 0. It's not the number 0, it's the function 0. Right. So it would just be drawn as the flat x-axis, basically. Okay. So is it going to be true, guys, if I take 2 derivatives of that and then add 3 times 1 derivative of that and then add 4 times that, am I going to get 0? Well, the zero vector itself is just this line. What is the slope of this line? Which would be the derivative, right? The derivative is represented as the slope. The slope of this is? Anybody? 0. And what would be the second derivative of this? 0. So I would agree that this is 0 plus 3 times 0 plus 4 times 0. I agree that that is 0 and it does check. So I would completely agree that it passes the zero vector check. Okay, so let's get into the closure under addition. So let's imagine that we have 2 solutions already that are in S. So let me call them F and G that are in S. By the way, did you notice how, so like on the video example with the symmetric matrices, I called the vectors, if you remember, it's in your notes, I called them capital A and capital B. Why? Well, that's because they're matrices, right? When I'm dealing with polynomials, what did I call them? P of x, Q of x. I try to choose letters, not that you have to use these exact letters, but I try to use notations that are compatible with kind of what universe I'm in. Right now, I'm in a universe of functions, right? That's what V is. So a good notation for functions might be F and G. If you chose to use Y1 and Y2 That's fine. There's no one right answer to that, but I'm just gonna use F and G. Okay, so let's see how to do this right up, and then guys, we've got some group work where I'm gonna let you guys practice this as well. How to write some of these up. If F and G are in S, then let's just write down what this means. If F is in S, it just means that F double prime plus 3F prime plus 4F is 0. And at the same time, G double prime plus 3G prime plus 4G is also equal to 0. Okay? And those are the individual functions F and G. What I would like to do is add them together and see if the result is still going to satisfy my differential equation, right? So then if I take F plus G double prime, quantity of F plus G double prime, plus 3 times the quantity of F plus G prime, plus 4 times the quantity of F plus G. Now here's the popular wrong thing that I see people do right now is they'll put equals 0 right here. Actually, no, we are trying to derive if it does equal 0 or not. I'm not ready to say equals 0 yet. I'm hoping that I can derive that. So how am I going to derive that? Just do a little bit of algebra here. Split this up. This is F double prime plus G double. We all know derivatives kind of respect addition. You can kind of break this apart, right? This is just F double prime plus G double prime plus 3F prime plus 3G prime plus 4F plus 4G. Just kind of split it all out. And spell that all out turn by turn. So it's kind of a mixed bag of F's and G's here that we end up with when we kind of expand that out. But what I'm given, so this is kind of what we know is up here. This was already stated. So I'm going to kind of reorganize these terms with all of the F terms in the front. So I'll put those together, right? So F double prime plus 3F prime plus 4F. I'll put that all together in the front and adding to that the G double prime plus 3G prime plus 4G. I'm just going to kind of gather everything in the natural way with all of the F parts together in the front, all of the G parts together in the back. And guys, this first part consisting of the F pieces is given as 0. And the second part, which is just all of the G parts added together, is also given as 0. And so now I'm in a good position to put my equals 0. Okay. Now, once I've kind of taken a breath and I've reflected on this calculation, I should make a final conclusion. And I always will be looking for this in your work, which is, what is the conclusion here? The conclusion is that F plus G is in S. I want to put a check on that and confirm that it's good to go. So that calculation shows it. You guys notice how I create a 1-column chain of equal signs here. And over on the left side, this is just white space over here until I get to the conclusion. This is the way you want it to look. You don't want to have stuff going on both sides of the equal sign. It's like the algebra is changing here and here at the same time. It becomes kind of hard to keep track of that. But try if you can to just go step by step, one thing to the next, to the next, to the next. Equal signs going right down the side there. That's the way you want your write-up to look. Kim?
So for the first part, like the Z,
Yes.
it for me looks similar to the new space thingy.
It looks like a null space thing in the sense that you have equals 0 on the right-hand side. It seems to be that's a common theme of these subspace calculations. Yeah, it is kind of like that, but what you need to realize, Kim, is that there is no matrix here. We are not even in a universe of matrices at all. null spaces are always about systems of equations that are solved through the use of matrices. And we don't have that on this kind of a setup. But it's a totally natural connection to make. It just doesn't really work. Yeah.
If the whole set of terms equal to a constant, would the zero check not go through at all?
Correct. All I have to do to screw up this problem is change this to whatever my favorite number is, right? And then it will not go through. The zero vector check would not be equal to 17. So it wouldn't pass that. And even if you ignored that and you just decided, I'm going to just try to go straight to the addition, well, you'd have this equation equal to 17, this equation equal to 17, and then by the time you got done with everything, you would have 17 plus 17, which does not equal 17 again. See, there's only one number in the whole world that when you add it to itself, just gives itself back again. And that is 0. And that's why it's so important that this has to be a 0 here, guys. If this is not a 0, I guarantee is not going to be a subspace. So some people might, it would be a fair question. Well, what if I'm an engineer? And what if my actual differential equation that I need to solve for my real world problem is this one? That would be a fair question. So, well, Dr. Anand, your whole subspace stuff doesn't work now. Right? Because I just said that if this is anything other than 0, it doesn't work. Well, we're going to learn about that in chapter 8. We're going to learn that even if this is a number other than 0, you can still solve it by first solving this equation. And then there's a second step we have to do to deal with this fact that this isn't really a 0. Yeah, so, yeah, Caesar.
So this might be like sacrilegious to ask, but since the scalar check will catch that mistake if it's equal to 17, why not just jump?
So the scalar check, you could, yeah, you could. There's nothing that says you have to do closure under addition first and then scalar multiplication. You can totally do that in a different order.
So it doesn't mean if one works, the other one will.
That's right. You can have examples where one works and the other, like that determinative A equals 0. The very first example, that failed to be closed under addition. But if we had done the scalar multiplication, it actually would have worked. So yeah, they are kind of independent of each other. Raphael?
Why are they equal to 0 again?
Because we assume here, right, when we start this off, that we're just grabbing out of the sky two functions that are already in S, meaning that they already make this differential equation equal to 0. So we're kind of writing this down almost like it's the assumption. And we're going from there. We have to have the correct assumption in place. Otherwise, yeah, the calculation isn't going to be doable.
Could you make the argument and say like, without having to do all the work, that they're gonna be 0 regardless?
I would want to see, this is kind of how you convince somebody.
Okay.
Right? I mean, yeah, I've been doing this for 25 years, so I probably say, yeah, I can see in my head, yeah, if I add those two, there's 0. Yeah, it's going to be 0. Right? But I think it's better for us to kind of write them all down first time through. Was there another hand I thought I saw? Pretty good. Okay, the scalar multiplication, let's do that real quick, and then we'll take a break. So the closure under the scalar multiplication part. Guys ready to get out your rubber stamp? Let K be in the real numbers and F be as above, right? So let K in the real numbers and F as above. Here it was P of X, but now we're in the universe of functions, so I'll write it as F. And then I'm going to just calculate K times F. This is being done kind of abstractly because we don't have an F specifically in our hands. We just have to write it as K times F, but I'm going to plug it in where I see the Y here. So it's 2 derivatives of that plus 3 times 1 derivative of K times F, and then plus 4 times just simply K times F. Okay, so I write that down. I already know that I want this to be equal to 0, but I'm not going to write equal 0 yet. or I'm kind of jumping to the punchline too quickly. Instead, I want to do algebra with this, the same way I kind of did some algebra up here. And if you were stranded on a desert island and the only way to get off was to tell me what kind of algebra could you do with that left-hand side, what would you probably think of? I would factor that K right out of there. Sorry, I have strange analogies. So you factor the K completely out, and that leaves you with F double prime plus 3F prime plus 4F. Exactly. And sure enough, what has ended up in these brackets is exactly what we were starting from about. Remember, F is as above, meaning whatever you wrote about F above, you can use. So I'm just going to replace that. It's just K times 0. And again, guys, if it had been, of course, K times 0 is equal to 0. If it had been K times 17, I would not have been able to say that it equals 17, right? So that's why that equals 0 is so critical. But then let's not forget our punchline here. I'll add this over here, guys. I'm running out of room, but I think I can squeeze it here. K times F is an element of S, and we check that one off. We check that one off. So this turns out to be a yes. It is a subspace. Awesome. Make some sense? Okay. Any questions about verifying these things? So if it's a null space, it's a fast yes. If it fails the 0 vector check, it's a fast no. Anything else, we have to think about it. Maybe we'll have to write out a calculation to verify it. Okay? But yeah, this means that whatever we're going to learn about vector spaces for these next 2 weeks is actually going to be helpful for studying differential equations, because the solutions, at least to this differential equation, and lots of others, forms a subspace. And so that means the vector space theory is relevant now for us to become, to equip us to study differential equations more effectively. Stay tuned for that. That's coming much later in the semester. All right, let's take a 10-minute break. I'm gonna let you guys stretch. I know this has been kind of mind-bending, but when we come back from the break, we'll practice even a little bit more, okay? So I'll see you guys in about 10 minutes. Stanford Road. Can you do that?
Yeah.
Maybe he can help us. I do have a question. Okay.
I just wanted to watch you now.
I get it. No, thank you for talking. No worries.
Also, are we gonna get back to our exam?
Yeah, I was gonna do that at the end of the class, so maybe you come on this or something. Is that possible? Okay, great, thanks. Thanks for your help with the board. And Oscar, if you could, just don't erase this. Side, thanks.
I really I think I got saved.
How do you do?
I did all right, but I didn't do as good.
Me too, bro. Me too. Bro, you say all right. You go like the high score. My friend do that. He got a high score in the class. It's like that's all right. I want that, bro.
I mean, occasionally, but it's not like
Now I guess because I have a point. Gracious. I already told you.
Yeah.
it's like an hour. And I also have to study for.
Yeah, I did. I mean, it's fun to me.
Like, that's the use. We love it.
Yeah.
Yeah, I think that's good. That's hard, I can be like, I sweat, I don't say
There was this picture. Interest. It'll be good regardless, like, so, he didn't.
I mean, he just has a.
I think the show I like.
Or that's like. It's nice to have a physical listening. I like the challenging ones. Yeah.
I love this, it's gonna, we're going older. I think, okay, I take it back. Please don't do it.
Yeah, that one was kind of, you know, one thing, I think this is a late to this.
How you gonna do it? And go this year. You know, do it. Wait, no, but it's not just something. I trust myself. Yeah, it's really, or I just go on.
Oh, I saw. That's really good. Oh, yeah.
And
Well, right after class, I'll be around, but it's only for like a half hour. The best time, when I have more time is tonight. After 5.
I have a class from 5:30 to like.
So I usually go to dinner at 7 and I come back again. So I come back usually around 8:30. So that's the best I can do the way my class schedule is I have classes kind of all day until 5:15. And other than these short little breaks between the classes, but it's not much.
Yeah.
Where every single time.
Note on your.
Yeah,
Did you see it?
I did see, you submitted it. Okay, great, great. That, no, you're fine. I'll be taking a look at that later. I'm so good at video science. It's just keep on so fun.
Oh, yeah.
Anybody know if it's been 10 minutes yet? I forgot what time I started the break. Man, I'll make it. You guys ready? Promise. I shouldn't make promises I can't keep.
Like, it's fun for me, but.
Maybe it's only just for me. Oh, yeah. Guys, on your tables during the break, I kind of went around and I passed out to you this group work number 6. So now here's the deal. Okay, is everybody paying attention to me on this? Because I've noticed in the past when I do this, people forget about this. I have put hints over here for these problems. So the first thing I'd recommend, like part A, you don't have to do it because we did it in class a few minutes ago. But on some of these other ones, like part E, you can skip it for right now. D and F, you should be able to just very quickly give me a thumbs up or a thumbs down. And then B and C might take a little bit more work, but overall, I think although there's a lot of parts to this group work, I'm only going to give you about 10 minutes to work on it because of all the hints that are over here. We should be able to boom, 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 try to knock it out. So if you could grab 2 or 3 other people, I'd like to get you up at the whiteboards though. There's markers all around the room, in the back, on the side, in the front, and see what you guys can do. And I'll come around and kind of look over your shoulder a little bit. Main thing is everybody should have a partner. Try not to work totally alone. I want you talking about these ideas. Grab that paper and grab a group. Any group you want.
Yeah. And then you have to define, well, for the addition, you have to define what each metric is, so 8 equals a negative 10. You have to get another one, so it'd be BT is equal to negative B, and you have to add up. Wow.
Should be.
I was looking at.
Okay. So this supposed to be capital A. Sorry. The first thing you might need to do is write down what a symmetric matrix is. I said in my head to see the video notes. No, I did this. So you need one.
Yeah, so you'll just define two
You can probably find an example with those.
Yeah.
Similar to rest.
And then B should be.
You wanna join it?
Yeah, sorry. You can join anything you want.
I'm sure everybody will be happy. We'll join those guys in the back. And those what are you guys looking at? Oh, yeah. So what does it say for the end? So the past answer. That's actually right. The only thing I would want you to do is just recognize something that it's located in one way. And for me, yes, it's still. Start, guys. That's really awesome. Well done. Anybody need help?
Or a six-up notation, X, Y.
If you feel, I would say total space, I would say what. So null space, what I would do. That's a unique answer. Not the zero budgets. The matrix that comes from that. So I would write that matrix in there and then.
C.
Actually, you don't do that. If it's a null space, you just.
Oh, well, we should do B first. Well, do we have to do the ones that were?
Yes.
Because A and B is kind of like already in the nose. Okay, let's just do C. Let's just do C.
Are you, what's so simpler?
That's it. So, I think that says see video. The reason for that is that this is the use metric one. The only difference is now on the right side. And so the question is gonna be, if you trace through those notes, does that make a difference?
Yeah, it's just.
Yeah.
If you assume that we is something.
Take the mind, make some positive, so.
Exactly.
So,
Without the minus. He's already done it. Transfer of the wave must be, so the negative of A must be.
Oh, wait, no, sorry.
And there would be a case, so you don't need this here. You can just say element, it's a null space, so it's a.
You can put the negative.
Here, I'm actually checking rows are under addition.
In front of it.
I need to see
This
this.
is in.
Oh, well, this is.
Yeah, maybe somebody else can. So, good job on. Zero.
No, I'm.
Exactly. Good job, good job, good job. Anybody need help?
Yeah.
Yeah.
Oh,
Yeah,
the matrix, I think.
So I would just put these.
Yeah, I think that crossing and they're gonna
Checking. For this.
It's like a double track.
Start.
So this is. Those are just called deep.
But what you have.
So
It's the same as HF, but HF.
Oh, right. In
Yeah.
that case.
And then, we already started.
It's just parabola, it fails because it.
So that's plus.
That's the one I was reading.
That's good, yeah.
But I think it does.
Negative one.
Yeah, you try.
If you add it together, you get zero.
Yeah.
two.
So then you're just gonna see it.
Pass.
Yes.
So your check.
That's it. If zero check fails, I'm just stop there. Perfect. That's perfect. We're gonna do C.
Really.
Trying this one. Super. Anybody need help? Great job, guys.
Like he said, like all we do
This is not actually a parabola. It's not quite a parabola.
No, it's not.
X squared equals y squared. If you take the square root of both sides of that. Actually, that. Plus or minus x.
X squared.
Plus or minus y squared. Actually not going to be a parabola. It's going to be.
Yes.
But I do want you to draw the picture.
It's a square root plus or minus.
Yes, it's a big giant X.
But are they just on the zero?
So now I have to think, we're not gonna be closed under addition and scale.
Yeah.
There's probably one in the notes that's also kind of like this.
I don't fail one of those.
It's gonna fail, so you're right about that. Yeah.
So, yeah.
Yeah, so this zero
How's it
vector,
feel?
well, the thing is, if you plug in. The zero vector is just this. If you plug zero into it, you would get zero.
Yeah.
And so you start to get the I would say, yeah. Let's write that. Here's your zero vector graph. What is this?
Unless.
That's the condition.
It'll be 0, 1.
0, 2.
Okay.
And then that's.
That's the condition to. Background. Because when you plug in zero into this line, it's 0, 1, 0, 1, it's there.
Yeah.
It gives you zero.
Yeah, as long as it fails.
You have to understand, this zero is not the number zero, it is the fun zero. It's this entire graph.
There's just a little space.
So,
I plug in here, I plug in 5, I plug in negative 8, 0.7, no matter what I plug in, I always get zero. I never get 1. Which means I do not satisfy it. Everything else we do, it just fails to do it, check it. That's why
It has to be a point on the thing, and if we use the
this would be great to show. Right, because.
I guess.
They actually get it like zero.
Yeah, so this already tells, I don't know. Is in us. Chat.
Yes.
So that's all we're doing.
Because what does it mean to be in us? This means it's to be skew symmetric. This is the skew symmetric definition. So if we have the J. Have the mixture and we check that same property, it's. It's the A plus B is still.
Red.
The beauty of this is us being at a 3 by 3 H cells. This could be 5 by 5, it could be 12 by 12. It really would still be true. Yeah, you're welcome.
Oh, no, we're never.
No, we would.
Zero check.
I think so, because it's 1.
That's 0, 2, but you're right.
Yes.
Hopefully.
Well, be careful about this. You don't just toss it on like a random.
Yeah, it's just, this is what.
How you done the talking about? And here you have. This itself is in S.
It didn't pass over.
What's the graph?
Because
It says draw the graph.
So therefore it has. Square root of. Or no, it's not a subset.
You actually get plus or minus. So it becomes.
And I should probably.
Both ones together.
Easy already proved with the zero, or with the no space. You can press.
Yeah, right here, yeah. Yeah.
Oh.
Because of the zero, like, I'm pretty sure you spelled zero.
Or if it passes at zero.
I think it does.
Yeah, like that, that's right there.
I think either way.
If it's F zero, it's equal to one. They can't get zero. Huh. Right? So that means. Even if it's
So when you get the added.
Yeah, so the only.
Well, you need one more example. It shows it.
So like this would be like nine. What is it?
Literally just be zero. So either one or two. Think about R2, right? Zero vector is just 0, 4.
Yeah.
And you're actually plugging it in for both next. And it does. Pass the zero. But just the zero vector.
Or-
Oh, we are skipping. F is.
You bet.
All right. Well, actually,
So the key thing on part B is that a symmetric matrix is going to
Anything
have.
else?
Okay, so this one here. It says
That's not equal to zero.
That's because in the video. I did-
I know what I'm saying, because it doesn't equal zero, it doesn't pass the intercept.
Because symmetric. Now we have to present it as negative.
It's on there, but I mean, why not? I mean, shouldn't it be yes, because it's the same rules we just applied to this? Well, actually, no, that only passes the zero check. I don't know about the other two. No, but like, you could prove this the same way, like. No, it doesn't mean that it's a subspace. It just passes the first. We just see on plus x, you would let x equal.
It's basically the
You
same.
would like let.
Except it has to be written down.
Yeah, exactly. So does that? Yeah, that would be K. That would be K.
Well, I think
What's the formula? Like K, subspace R.
So. I draw the zero back. So when I plug zero into this red curve, do I get one?
K of L.
It does.
Yeah, the zero check actually does fail. And so you're actually, that's my fast answer.
You get the
Because
zero.
vector check
So I think I'm passing skill.
Yeah.
It's everyone going to hold his line.
Looks good, looks good. I love everything you see here.
We're supposed to do G.
I was gonna just let people, if they had time, you could work on it. It does work.
Yeah, this
it
is
does.
our proof for it.
Hey, that's great. Good job. Good job. Yeah, I like it. I like it.
Because it fails, we can look to the scalar, right?
Hey, guys. If I could get everybody's attention, I've had a chance to kind of look all around the room, and I know not everybody totally finished everything, but everybody has done a really good job on a good number of these items. I'd like to kind of bring this to a close so that I can kind of have the last part of the class today to kind of pitch a new idea to you real quick before we kind of get out of here for the day. But really, really good job on this group work. I really appreciate it. Let's go ahead and gather back up, and we can always review this tomorrow in the Canvas solutions that are posted online.
Yeah.
Want me to just look real fast?
Unless he wants us to erase.
That's okay. He had, yeah. I don't know. Excuse me, cut out our part. Yeah, fails. Like if you look at it, it's also fails equals a very good.
This is what you should.
Okay. Yeah, just thank you guys. Thank you so much. Thank you for helping with the erasing too. I really appreciate it too. Big help. So guys, just real quick, the one that was x squared equals y squared, right? The key thing about that is it's actually two lines. It's not just one line, it's two lines that forms like an X. It's kind of tricky, but your set S is actually a giant S. X, sorry. It's a giant X, and that fails to be closed under addition. If I take something like the 0.11, that's in S, but I also have the point -11, which is in S. And if you add them together, you end up at 0,2, which is not in S. It actually fails the addition property. So it's kind of a little bit of a weird one there. Okay, but anyway, guys, the solutions to these are posted in Canvas. Like I said, a lot of the homework for Thursday is either very similar or almost identical to some of the ones that we've already practiced on. Okay. But those solutions are in Canvas. I definitely encourage you to go back to those. I want to spend the last, whatever it is, 10 to 12 minutes here pitching a new idea to you. I think you're going to like this. This is going to take us until Thursday to really get into in great detail. But I'm going to start talking about it right now. It is something called spanning sets. I want to talk about something called spanning sets. So here is the idea of spanning sets. The idea is that we want to form subspaces by the bushel barrelfuls. I'm going to show you a way of making subspaces left and right. Piece of cake, right? So the idea is, given a vector space, I'll call it capital V. So you start out with your big universe, whatever it is, could be matrices, could be polynomials, could be calculus functions, could be physics vectors, whatever V is, and you are going to grab a handful of vectors. You're going to grab a handful of vectors. I'll call them maybe V1 and V2 and ... up to Vn from V. Okay, so my objective, my goal right here, guys, is gonna be, I'm gonna try to create subspaces by the billions. So what's my idea? My idea is, let's just grab a handful of vectors. Now, the honest truth is, that handful of vectors by itself is probably not a subspace. Just the odds are against it. First of all, if you did not grab the zero vector, you know it would not be a subspace because the zero vector must be in any subspace. But also, if you just grab a handful of vectors randomly out of your big universe, maybe a couple of polynomials, maybe a couple of matrices, whatever it is, you grab a handful of these vectors, chances are they're not going to be closed under addition yet. And chances are they're probably not going to be closed under scalar multiplication yet. For example, let's suppose that you're in R2 and you grab the vector 1, 1. Well, that's not going to be closed under scalar multiplication unless you also grab 2, 2, and 3, 3, and pi, pi, and negative square root of 2, negative square root of 2. You would have to grab more than just this one vector alone to expect to make a subspace. So you know what we're going to do here, guys? We're going to take that handful of vectors that we grabbed, and we are going to then throw a whole bunch more vectors into that set to force it to be closed under the operation. We're going to force it to be, we're going to say, well, maybe it's not closed. If I grabbed the vector 1, 1 and I grabbed the vector 2, 2, we're going to force it to be closed by throwing in 3, 3. Right? We're gonna take many, many more vectors than just this handful. And that's exactly what we're gonna do. So let's write that down. Grab a handful of vectors from V, and I'll just say, close it up under the addition and scalar multiplication. In other words, we're going to close it up sort of by design so that it's closed under the operations. We're going to quote unquote close it up. So I need a couple of definitions here to kind of talk more professionally about this rather than just casual. So a quick definition, a linear combination. So I want to define what's called a linear combination of vectors is an expression of the form. Okay, so let me slow down just a little bit. A linear combination of vectors is an expression of the form C1 times V1 plus C2 times V2 and plus dot 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 plus Cn times Vn. This is what's called a linear combination of those vectors. Okay. Notice that in this box, I am taking my handful of vectors and I am doing two types of operations. I'm doing some scalar multiplication and I'm doing some addition. It's exactly the two operations in a vector space. Addition and scalar multiplication, nothing else. I'm not doing any dividing. I'm not multiplying vectors together. It's all just addition and scalar multiplication. Now, what I'm going to do when I close up my handful of vectors is I'm going to throw all of these kinds of expressions that I could make out of my vectors into my set. That's what I'm going to do. And when I do that, I get something called the span of those vectors. And that's the second definition I want to kind of put side by side with this one. Second definition here, guys, is that the set of all possible linear combinations of V1, V2, and dot, dot, dot up to Vn, the set of all possible linear combinations of those vectors is is the span of the vectors. It is the span of those vectors, and there is a notation for this. It is just denoted, guys, with the word span in front of, whoops, sorry, span of, and then I just get my braces out and I list the vectors into these braces. The span of those vectors. The set of all possible linear combinations of my vectors, that forms what's called the span of my vectors. And the big result is that if I start off with my handful of vectors, that's probably not closed to begin with under addition and scalar multiplication. It's probably not a subspace yet. But if I grab that handful of vectors, guys, and if I form all possible linear combinations of those vectors, guess what? I'm going to be making it a subspace by design. By just saying, I'm going to close it up under it. It might not be closed to begin with. I'm going to throw in these additional linear combinations so that it becomes closed under addition and scalar multiplication. And that is the big result here. I'll state this as a theorem, right? The span of V1, comma, V2, comma, dot, 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 up to Vn always forms a subspace of V. It always forms a subspace of V. That's right. That's right. It always forms a subspace of V. So you guys can probably already kind of picture the start of our second midterm in your heads. He's going to ask us some questions. There's going to be a vector space and there's going to be a set. He's going to say, does it form a subspace of V? What we've been doing all day today, right? Right. If you can take the set that I gave you, and if you can recognize that it is just a span of whatever, doesn't matter what it is, anytime you take the span of anything, it always is guaranteed to form a subspace. I have just given you another fast yes. If you can recognize that it is a span of whatever, I guarantee you that it's a subspace. So we need to do some examples of this, and I will have to, of course, mostly do that on Thursday. But since we just did group work number 6, I'm going to do the one that I wrote skip for now on with you right now as kind of the last thing for today to kind of illustrate this idea. Okay? So what does part E of this group work number 6 say? Well, the vector space was P2 of R. And S was given as the set of AX squared plus BX plus B minus A, such that A and B are real numbers. And the question is, does S, so I'll just say, is S a subspace? It's the same question we've been doing for the last 2 hours, basically. Is it a subspace? That's the question. I am going to convince you that the answer to this is yes. It's not going to be yes because it's a null space. By the way, null spaces require you to have a matrix around. If I see that my universe is polynomials, if I'm working in a universe of polynomials, I don't want to hear anybody talking about a null space. Null spaces refer to matrices, vectors with slots that solve a system of equations. That's not what we have here. Okay. We could check that this is closed under addition and scalar multiplication. But would you guys like to see the fast answer? I know you do. We want to, because I'm excited. I mean, I've got to keep my momentum going here. What I'm going to do, guys, is I'm simply going to rewrite this just slightly. I'm going to factor the A out of wherever I can pull the A out of. So there's an x squared here and then a -1 at the end. And then I'm gonna do the same thing with the b. I'm gonna factor the b out of wherever I see a b. There's an x here and then a +1 here, right? I'm just re-expressing it like that, such that a and b are real numbers. Now, if you look at the definition of the span over here, the constants that I was putting in front of my vectors were C1, C2, C3, and so on, but there's nothing that says that the constants have to be labeled as C1, C2, and C3. This A is kind of sitting in the spot of C1. And this B is kind of sitting in the spot of C2. If you think about it, guys, this is C1 V1 plus C2 V2. It is exactly the set of all possible linear combinations of those two polynomials. In other words, if we just think about it for a second, this S that we wrote down, it is the span of the first vector was x squared minus 1, comma, the second vector is x plus 1. And because it is a span, it forms a subspace, for sure. Automatically, by this theorem, anytime you take the span of anything, I'm going to say that about 100 times on Thursday. Anytime you take the span of anything, you always get a subspace. So this is kind of a clever way to do part E from that group work. That make some sense, guys?